All the machines are made up of elements, or parts and units. One of the commonly used machine elements are gears. And in this video, we are going to talk about gears, and I am going to discuss the first half of the topic, and later on Ms. Osias will take over. Now, let us define gears. Gears are toothed members which transmit power and/or motion between two shafts by meshing without any slip. They are also called positive drives. In any pair of gears, the smaller one is called the pinion, as you can see, and the larger one is called gear, the material of which is driving the other. When pinion is the driver, it results in step-down drive, in which the output speed decreases and the torque increases. On the other hand, when the gear is the driver, it results in step-up drive, in which the output speed increases and the torque decreases. Functions and applications of gears. Gears have various functions as precision component parts on a machine, such as gears for setting the rotate speed. Gears can adjust the rotating speed of power. Application: gears on motor engine. The gears regulate the power by giving certain gear ratios. Gears for transmitting power. Gears can transmit power with interconnected gears without causing slippage. Application: at a lathe machine. A lathe is a machine tool that rotates a workpiece about an axis of rotation to perform various operations such as cutting, sanding, knurling, and drilling. Gears for changing torque. Torque is rotating force that produced by an engine. It is for acceleration. To adjust the torque can be done by providing a gear. Application: crankshaft drive of an engine. Gears for changing the power direction. Besides gears can adjust the speed to change torque, it can also change the direction of power. Application: it can be found on dam gates or reservoirs. So, where can gears be found in industry? Gears are used in tons of mechanical devices, and they are commonly found in automobiles, clocks, pumps, watering system, household appliances, power plants, material handling systems, aerospace and aircrafts, railways, and trains. Moving on to the classification of gears. Gears can be classified according to the axis of the shafts. And here's three of them. Parallel axis gears, intersecting axis gears, and non-intersecting or non-parallel axis gears. The parallel axis gears involve two axes which are parallel to each other: types: spur gear, herringbone gear, rack and pinion, pin gearing. The spur gears have their teeth parallel to the axis, used for transmitting power between two parallel shafts, simple in construction, easy to manufacture and cost less, have highest efficiency and excellent precision rating, used in all types of trains. Also, there are two primary types of spur gears: the external and internal spur gears. First, the external spur gear have teeth cut on the outside surface of the meeting cylindrical wheels, and the teeth point away from the center. The input and output shafts move in opposite directions. Functions: for speed reduction and torque multiplication. Applications: in washing machines, blenders, aircraft engines, trains, and even bicycles. Internal spur gear has teeth cut on the inside of its rim, and the pinion is housed inside the wheel. Both the input and output shafts rotate in the same direction. Function: provides a compact drive mechanism for transmitting motion between parallel shafts that rotate in the same direction. Applications: often used in applications involving planetary gear drives and gear couplings. Another type of parallel axis gears are helical gears. Helical gears have teeth inclined to the axis. They are used for parallel shaft drives, and for the same reason, their teeth are longer than spur gears and have higher load carrying capacity. Their contact ratio is higher, and they operate smoother and quieter than spur gears. Functions: generate large amounts of thrust and use bearings to help support the thrust load. Applications: automobile machine tool gearboxes, steam, and gas turbines. Herringbone gears are a specific type of double helical gear, a side-to-side, not face-to-face combination of two helical gears of opposite hands. Function for transmitting power between parallel shafts. It was developed to overcome the disadvantage of the high-end thrust that is present with single helical gears. Applications: coal cutter and aerospace engine. Rack and pinion is a type of linear actuator, comprises a circular gear, the pinion, engaging a linear gear, the rack, which operate to translate rotational motion into linear motion. The tooth can be spur or helical. Functions: converts rotary motion into translatory motion or vice versa, and they are usually found in steering systems. Pin gearing is a form of toothed gearing. One of the wheels carries cylindrical pins which mesh into the spaces between the teeth of the other wheel. Function: for transmitting motion or power, reduces costs for rotating and linear drives. Applications: vertical tower parking, large transport trolleys, casting lines, and water gates. Another classification of gears are intersecting axis gears. These gears involve two axes crossing at a point. General applications include rotation, power, transmission of bevel gears. So bevel gears are used for transmitting power between intersecting shafts, can operate under high speeds and high loads, and their precision rating is fair to good. Their good choice is for right angle drive of particularly low ratios. Functions: change the spatial direction of rotation. Applications: differential drives and hand drills. Crown bevel gear is a type of bevel gear also known as contrate gears. These project at right angles to the plane of the wheel, which makes the teeth resemble the points of a crown, giving the gear its name. Function: allows a rotary motion to be shifted 90 degrees. Applications: used for trains on uphill tracks, roller coasters, locking doors on tracks, and car steering wheels. Another type of bevel gears are spiral bevel gears. They have curved tooth lines. Due to higher tooth contact ratio, they are superior to straight bevel gears in efficiency, strength, vibration, and noise. More difficult to produce, and also because the teeth are curved, they cause thrust forces in the actual direction. Functions: ensures smooth, reliable transmission, ideal for high-speed, high-torque applications. Applications: vehicle differential. Next classification of gears are non-intersecting or non-parallel axis gears. These gears involve two axes which are not intersected or parallel. Types: hyperboloidal, hypoid, screw gears. Hyperboloidal gears. Hyperboloidal gears are essentially regular spur gears with their top and bottom twisted in the opposite directions. Functions: used to transform rotation between shafts with non-parallel and non-intersecting axes. Applications: spatial gear sets of spheroid and helicon types. Hypoid. A hypoid is a type of spiral bevel gear whose axes do not intersect with the axis of the meshing gear. The shape of a hypoid gear is revolved hyperboloid, whereas the shape of a spiral bevel gear is normally conical. Functions: a higher hypoid offset allows the gear to transmit higher torque. Applications: power transmission products, rear drive automobile drivetrains. Screw gears, sometimes called crossed helical gears, are hyperboloid gears that allow the skew mating of the gear shafts. A special case of a screw is the so-called worm gear. Functions: used in motion transmission between non-intersecting shafts. Applications: designed for moderate torques and speeds. Example given: for drives for machine tools. Worm gear is a type of screw gear. It is a screw butted up against what looks like a standard spur gear with slightly angled and curved teeth, comprised of a steel worm and a brass wheel. Functions: you can use it to either greatly increase torque or greatly reduce speed. Applications: elevators, crushing machines, and speed reducers.
Gear ratio formula. Gear ratio is calculated by dividing the output speed by the input speed or by dividing the number of teeth of the driving gear by the number of teeth of the driven gear. For example, let's say that the smaller driving gear in our system has 20 teeth and the driven gear has 30 teeth. To get the gear ratio, we can divide the driven gear, which is 30, over the driving gear, which is 20, which results to 1.5. For more reference, here's another problem
All
for
right, so
gear
today we're
ratio.
going to be going over calculating the gear ratio. So I have two gears here. We'll say that the larger gear would be the input gear, and we can we'll say that the second gear, the smaller gear, is going to be our output gear for the sake of this problem. And let's go ahead and say that I counted up the teeth, and for the sake of this example, we'll say that the input gear has 40 teeth, and the output gear has 25 teeth. This is not the actual amount of teeth that each gear has. But for this problem, we use 40 teeth and 25 teeth as our example. All right, so when we're calculating gear ratio using the amount of teeth that each gear has, we need to remember that the formula we're going to be using is the number of teeth of our output gear in the numerator, and then in the denominator we're going to have the number of teeth of our input gear. Okay, so in this problem our output gear has 25 teeth, so that is going to be going in the numerator for this problem. So I've got 25 and then over, and then the number of teeth of the input gear. In this problem we had 40 teeth for our input gear, so 25 over 40 is our gear ratio. We now need to simplify this down. So I'm going to try to find the greatest common factor. If I can't find the greatest common factor, I'm just going to find any factor that I could divide the numerator and the denominator by. In this case, I'm going to go ahead and divide by 5, the numerator and the denominator. So I'm going to divide each of those numbers individually by 5. Okay, that way I keep my ratio the same because I'm doing the same thing to the numerator that I'm doing to the denominator. So 25 divided by 5 would leave me with 5. And then 40 divided by 5 would leave me with 8. And then I'll just double check one more time to see if I have any other common factors, anything I can divide both numbers by to see if I can simplify further. In this case, I cannot. So my gear ratio ends up being 5 to 8. That can be written as a fraction, 5 to 8. I also could write it in this format, 5 to 8, or I could write it exactly how I'm saying it, 5 to 8. Okay. Now, if I want to know how many times my input gear is going to turn compared to how many times my output gear is going to turn, that's when I now have to take my ratio of 5 to 8 and I have to think about it a different way. I have to think about it in terms of the number of revolutions. When I'm looking at a gear ratio in terms of the number of revolutions, the formula that I use is the revolutions of the input in the numerator, and then the denominator goes the number of revolutions of our output gear. Revolutions are the number of times that the gear turns in a complete circle. One thing you want to note out is when we're talking about the number of revolutions, the input gear is the one that goes in the numerator up top, and the output goes in the denominator, which is different than when using the number of teeth. So since I've already calculated the gear ratio using the number of teeth, which was 5 to 8, I'm now going to go ahead and look at the number of revolutions with my gear ratio. So in this case, the input gear is going to turn 5 times, because 5 is in the numerator. So my input gear will turn 5 times for every 8 times that the output gear turns. For every 8 times the output gear turns. All right, and now looking at my original gears, this kind of makes sense because we see that my input gear is a larger gear compared to the output gear. So if I were to turn the input gear one full time in a circle, the output gear is going to end up turning more than one time around because it is the smaller gear. And I can see that with my ratio of 5 to 8, that if I were to turn the input gear 5 times, then the output gear is going to end up turning more than 5 times. And in actuality, it ends up turning 8 times based on what I calculated with my gear ratio. So this particular gear ratio would end up going from a slow rotation in the input to a fast rotation in the output. So from the input to the output, the speed ends up being increased. So this would be a gear ratio that would provide us with more speed. All right, but then remember that the trade-off is when you get more speed, the inverse is you end up getting less torque or less power. So if you had a robot that you wanted to use that was going to go really, really fast, this might be a gear ratio you would like to use. But in doing so, your robot's not going to end up being as powerful as it could be. So you get more speed, but you end up getting less torque, less power.
And now let's move on to the simple parts of gear.
The addendum is the height by which a tooth of a gear projects beyond the standard pitch circle or pitch line. Also, the radial distance between the pitch diameter and the outside diameter. The diametral pitch of 4 tooth per inch 24 tooth pinion is to drive a 36 tooth gear. The gears are formed using the 20-degree full depth inflow system. Find the addendum. To solve for addendum, we can divide 1 over the diametral pitch, which is 4. That equals to 0.25 each. The addendum is a radial distance from the pitch circle of a cog wheel or worm wheel to the bottom of the space or groove. With similar problem as find out the addendum, to solve for the addendum, we can divide 1.25 by the diametral pitch, which is 4. That equals to 5 over 16 or 0.3125 inch. One of the parts is the axis of revolution of the gear, where the shaft passes through. Teeth. It is the jagged faces projecting outward from the circumference of the gear, used to transmit rotation to the other gears. The number of teeth on a gear must be an integer. Gears only transmit rotation when their teeth mesh and have the same profile. Sample problem number 4. A pinion gear with 22 teeth and a module of 6 millimeters has a rotational speed of 1,200 rpm and drives a gear at 660 rpm. Determine the number of teeth on the gear. Next is the pitch circle, the circle that defines the size of the gear. The pitch circles of two intermeshing gears must be tangential so that they can intermesh. The pitch diameter refers to the working diameter of the gear, aka the diameter of the pitch circle. You can use the pitch diameter to calculate how far away two gears should be. Sample problem number 5. A 22-tooth gear has AGMA standard full depth involute teeth with diametral pitch of 4. Calculate the pitch diameter. To solve for the pitch diameter, we can divide 22 by the diametral pitch, which is 4. That equals to 5.5 each. Diametral pitch. It is the ratio of the number of teeth to the pitch diameter. Two gears must have the same diametral pitch to mesh. Circular pitch is the distance from a point on one tooth to the same point on the adjacent tooth, measured along the pitch circle. Sample problem number 6. A gear drive consists of two gears A and B and has a velocity ratio of 1.5. Gear A, the smaller of the two gears, revolves at 126 rpm in the clockwise direction and has a 28 p. Module. It is the ratio of the reference diameter of the gear divided by the number of teeth. Sample problem number 7. A pair of gears has been designed with a velocity ratio of 3.20. The pinion has 20 teeth and the circular pitch is 78.54 millimeters. Determine the module of the gears. The pressure angle of a gear is the angle between the line that defines the radius of a pitch circle and the point where the pitch circle intersects a tooth and the line tangent to that tooth at that point.